Hello, I'm Michele Cooke, and I will lead off this presentation, and a little later you'll hear from a few of my collaborators listed here. Our presentation is on what subduction zone margin landscapes and seascapes can tell us about the system's processes and energy budget. In this talk, my collaborators and I will outline ways that surface processes of erosion, sediment transport, and deposition interact with deformation processes within subduction zones. This deformation includes faulting processes, both those along the subduction zone interface and faulting within the forearc, as well as deformation associated with material and heat transport within the volcanic arc. Additionally, I've listed climatic processes that interact with each of these other systems. All of these processes act across a wide range of timescales and impact the topography that drives the sediment transport. Consequently, when we investigate a coastal sediment record, we need to distinguish the fingerprints of large, short-duration events, such as tsunamis, from the dominant inter-event processes of storm deposits that may vary in size. At the same time, large events such as landslides and volcanic eruption can perturb the sediment transport system and erase more subtle records of inter-event erosion and sedimentation. I also want to note that the image of Mount St. Helens eruption that was triggered by a landslide highlights the relationship between deformation and surface processes, which is multidirectional. Surface processes can also impact deformation. Luca will now describe a very interesting example of the interplay of subduction zone interface deformation and submarine sediment transport.
Thank you, Michele. I would like to illustrate these interactions with an example linking processes that operate at very different timescales. On the one hand, surface processes shaping the landscape over hundreds of thousands of years, and on the other, deformation from the earthquake cycle on a 102,000 year timescale. Here we will focus on the signature of wave erosion, which can erode uplifting bedrock in shallow water, leading to the development of an erosive shelf between the shelf break and the coastline. For the earthquake cycle, we focus on the down dip end of high coupling, or the locking depth in the picture, and its position respectively to the surface features. So keeping track of the shelf break, the coastline, and the down dip end of high coupling, we can inspect different subduction sites. And we see that the shelf break appears to be a better guide for the position of the locking depth than, for example, the coastline. This is visible in Cascadia in the central figure on your screen, where we plot the down dip end of coupling from interseismic surveys, and we see that it corresponds to the shelf break. In the top right of your screen, you see the rupture extent of the Tohoku Oki earthquake in 2011, which stopped around the position of the shelf break indicated by a black line. Or in the bottom right, we see the down dip end of smaller magnitude 7 ruptures that also stop underneath the shelf break. In these three sites, the shelf break is a good guide for the position of the locking depth. But is there a more global signal for this? To investigate that, we compiled the locations of shelf breaks, coastlines, and locking depth around the Pacific, and we see a systematic collocation of the shelf break with the down dip end of coupling, with the coastline offset landward. This is represented in the figure on the x-axis. You see at 0 the position of the down dip end of coupling, and in blue the average distribution of shelf breaks clustered above this down dip end of coupling, and in orange the position of the coastline removed landward from it. So going back to the initial cartoon view of our simple system, we need a zone of uplift in order to uplift rocks in a zone of shallow water erosion. In order to do that, we need an uplift hinge line with positive uplift toward the land at the shelf break, and therefore around the position of the locking depth as well, as our observations indicated. The question would be, how would the long-term deformation be informed by the short-term earthquake cycle here? And Jean-Arthur will now propose a conceptual model to give meaning to this long-term uplift.
Thank you, Luca. So this question of how short-term deformation might be reflected in long-term landscapes is a particularly interesting one, because our usual view of the subduction seismic cycle involves slow interseismic, say, downwarping of the upper plate that is mostly fully compensated by the next coseismic strain release, as illustrated on the diagram on the right, with no net creation of topography. But that's clearly not what we see at real margins. So to conceptualize how the net sum of deformation over many seismic cycles might lead to some permanent uplift, we can think of the upper plate as a diving board in a swimming pool. The interseismic phase would be the downwarping induced by a diver standing on the diving board for a very long time, sufficiently so to trigger inelastic deformation mechanisms wherever the curvature of the plate is quite strong. So this is what's illustrated here in the lower left part of the slide, with areas undergoing very strong deformation induced by sharp displacement gradients experiences plastic yielding, so net dissipation of elastic energy, while the rest of the plate is storing elastic energy. So what will happen when the diver finally jumps off the board or when the next massive coseismic rupture occurs is that the bulk of the elastic energy will be released, except in those areas where energy has been dissipated. So what that means is that the net sum of the deformation accumulated slowly interseismically and coseismically does not amount to zero, but leads to some permanent deformation whose spatial pattern triggers, or I'm sorry, mimics patterns of the interseismic loading. In the case of a simple elastic thin plate or elastoplastic thin plate, the permanent deformation mimics the curvature of the downwarping induced interseismically. So for the case of subductions, what this means is that potentially at every seismic cycle, we have a small increment of plastic yielding that might occur close to the locking depth, where we have very strong displacement gradients, therefore strong deformation, therefore strong stresses, and that these tiny plastic non-recoverable increments might build up over time to give shape to this permanent long-term uplift, which is what the wave erosion feels. So to bring this back into the subduction framework and the problem of the hinge line collocated with the locking depth, Lucile will now discuss how these concepts might apply.
Thanks, Arthur. Now let's come back to this representation of a subduction zone. We know that most of the deformation is elastic during the earthquake cycle. Strain slowly accumulates during the interseismic period to be dramatically released during an earthquake. Over the short term, the distribution of vertical deformation, here what matters is uplift, is locally controlled by strain accumulation during the interseismic period. More specifically, as strain accumulates on the plate interface, this is a shape of surface deformation. The ground sinks close to the trench, while we see uplift closer to the shore. What matters here is the location of the hinge line, which limits the region of uplift and subsidence. This location is controlled by the maximum depth of the locked region, also called locking depth. Now, if we consider that a tiny fraction of the interseismic deformation pattern is plastic, the residual vertical deformation due to cyclic strain accumulation would have the same pattern over the long term. The uplift hinge line obtained from a short-term process, such as interseismic strain accumulation, will persist in time into the long-term uplift pattern. During the platform evolution, the shelf break resulting from the interaction of wave-based erosion and uplift will be anchored at this hinge line, and the shelf itself will grow landward by coastal retreat. This is an example of how a marker of long-term deformation, such as the shelf break, can reflect the critical information about short-term interseismic deformation. This could serve as a blueprint for a collaborative approach to subduction zones. In particular, we could think of it in terms of energy budgets, as Michele will show you now.
Thanks, Lucile. We can conceptualize the subduction zone energy budget as having inputs and sinks. One of the major inputs to the subduction zone is the tectonic work of contraction across the margin. For example, margins with faster contraction rates may have greater rates of energy input to the system. Other energy inputs to the subduction zone include heat flux and mass transport within the volcanic arc. The growth of that topography adds to the potential energy of the system. Meanwhile, the faulting components to the subduction system, both along the megathrust and within the fore arc, provide energetic sinks for the system in the form of frictional heat from sliding and seismic energy. When we add some energetic terms associated with surface processes, we start to see how the landscape and seascape provides energetic inputs and outputs and link to the magmatic and faulting components of the subduction system. The terms that we've listed here in this first order formulation include potential energy of precipitation mass added to the system and energetic sinks of work against gravity and internal deformation. We also recognize that this is a very simple treatment of a very complex system. We could add many more terms to this formula when we consider, for example, energetic contributions of crystallization within the magma chambers, energetic loss of production of damage within fault zones, and energetic sink of grain abrasion and wear during transport. Even this first order conceptualization of the energy budget provides a framework for investigating the relationships between processes that act across a wide range of both temporal and spatial scales. We can also use this framework to map how findings from one study, such as the relationship between locking depth and shelf break presented here, map into and impact the entire subduction zone system. Thank you.